Welcome. In the following set of videos, we're going to introduce ourselves to a topic called graph theory. If you've never heard of graph theory before, it has to do with dots and lines. It doesn't have to do with maybe the traditional graph, like plotting a curve. That's not what we mean by graph theory. To get us started, we're going to look at a problem from section 1.3 of the Puzzling Adventures of Dr. Echo. This problem is called the odd doors problem. So Lawrence Terrence III has a problem. He's recently had his father pass away, and his father was a bit of a mathematician. He hid a cache of jewels in one of two underground labyrinths. So Lawrence knows the following facts about the labyrinths. The first fact: the jewels that his father hid are in a room with an odd number of doors. So if you're in the room with the jewels, you look around and you count the number of doors, there would be 1 door or 3 doors or 5 doors, 7 doors. All of the odd numbers are possible. The even ones are not. The second detail: only one of the two labyrinths has a room with an odd number of doors. So if we extrapolate on that a little bit, the one labyrinth has a room with an odd number of doors, while the other labyrinth has only rooms that contain an even amount of doors. The final thing that Lawrence knows is that one of the labyrinths has 2 doors leading into it from the outside, while the other labyrinth has 3 leading in from the outside. Now, these labyrinths are quite straightforward. They just have rooms and doors. There's nothing else to them. You might think of, well, there's some hallways. Well, we'll count hallways as rooms as well. So you enter, and the only thing that's separating the rooms are doors. So unfortunately, it's going to cost a small fortune to explore each of the labyrinths. Say that these labyrinths are underground and we need to dig them up, and the jewels are worth $2 million. So it's really valuable to grab those jewels, find that room with an odd number of doors, but the excavation to dig up each of the labyrinths will cost $1 million each. So if we dig up both of the labyrinths and then find the jewels, we'll just break even and there won't be a point. But if we find the correct labyrinth to dig, we'll net $1 million. So, can you solve this problem? Pause the video now, try, and as a hint, maybe read what a graph is. A graph can kind of help us with this problem. It might not be clear right away how it helps us, but a graph is a collection of dots and lines. See if you can think of a way before we go forward that might help us solve this particular problem. All right, let's discuss the definition of a graph. So a graph, like we were saying, is a collection of dots and lines. So the dots are called vertices formally, and the lines are called edges formally. Now, the one rule that we have to make sure we abide by to build a graph is that every edge or line is terminated by a dot at each end. So when we draw our graph, if we're going ahead and drawing, let's say this is our dot, and we're drawing a line, that line has to end at another dot. So that's a successful graph. Now, you could also have some funny graphs. You could have a graph with multiple edges joining the same 2 vertices. So that's allowed. You could have another graph where you have 2 edges between the same 2 vertices. You can also have a graph where you have a self edge. So you can have an edge that comes back to the same vertex. So these are all examples of graphs. You can even envision all of these together as one graph if you like, because graphs don't necessarily have to be connected. So you have three disconnected pieces of this particular graph, or you could view each one individually as a graph itself. So those are graphs. Let's draw one more graph that's a little more interesting. So you could have lots of edges. You could have a square and then more edges coming out, as long as each edge ends and begins at a vertex. Let's draw some things down that are not quite graphs. So if you have just a vertex and an edge that just doesn't go anywhere, that's not a graph. Now, if you just had a vertex, so if we go back over here, if we just had a vertex, that is a graph. You can have a graph without edges, that's perfectly fine. So some other ideas that wouldn't be graphs, you could have something that you're starting to make a graph and then you don't end an edge at a vertex, and then it's close to being a graph, but it's not technically a graph by the definition. Okay, so let's move on to some further definitions below. So an edge that is joined to a vertex is said to be incident to that vertex. So this word incident is going to be important moving forward in this video. Let's draw a picture of that. Okay, so there's my edge and there's my vertex, and these two objects are incident to each other. The edge is incident to the vertex, and also the vertex is incident to the edge. So if we keep drawing this graph, we will draw another vertex and another edge. Now, the edges that are connecting to this middle vertex, they are said to be adjacent. So also, the two vertices that are here, let's say this vertex and this vertex here, they are also adjacent. So objects that are directly connected are incident, and objects that have something in between them are adjacent. You can also say that this vertex is an endpoint of that edge, or this vertex is an endpoint of this edge and that edge. The most important definition going forward is incident. We're going to count the number of edges that are incident to vertices in the next definition. Okay, so in definition 3, we get the idea of a degree of a vertex. So what we do is we count the number of edges that are incident to that particular vertex. So if you have a vertex, let's call our vertex V, and let's say there's 5 edges coming out of it. Then the degree would be 5. So if you're zeroing in on that particular vertex, you can say that DEG for degree computes as a function of that vertex. So we input the vertex and then we output the number of edges that are incident to that vertex. And of course, if this is a proper graph, we would have all of these edges connecting to vertices at their endpoints. All right, so that leads us into our first theorem in graph theory. Call it the parity theorem, or an equivalent statement is the handshaking lemma. So both of these are used, they're both equivalent to solve whichever problem. Sometimes you might find the language in the parity theorem a little bit more convenient, or other times you might find the handshaking lemma a little bit more convenient. So the parity theorem says that the sum of the degrees of all the vertices, so the sum of the degrees of all the vertices, is equal to twice the number of edges. So capital E is representing the number of edges in a particular graph. If we multiply that number by 2, we always get what we call the degree sum. So this makes sense because each edge, when you add it into the graph, it contributes 2 to this amount because it has 2 endpoints. So thus you get this equation that gives you the total degree, comparing the number of edges. So we can also talk about the handshaking lemma. So every graph has an even number of vertices of odd degree. Okay, so this is another way of talking about that equivalence from above. So if we just scroll back up, if we think about what it's saying, we have an even number of vertices of odd degree. So if you were to take all of the vertices and add up the degree like we're doing here, that number is, well, even or odd, they're integers, but let's investigate that for a moment. Let's say the first number that we add in is odd, and then the next number that we add in is even, the next one is odd, and the next one is odd. If the graph had 4 vertices, and this was the scenario, something wouldn't make sense here, because the 3 odd degreed vertices here would make this total sum an odd sum. But we have to get twice an integer. So this sum has to be even, and we can't have an odd number of odds. That's what the handshaking lemma says. It says that we have to have an even number of odds. So the scenario that we wrote down here wouldn't be possible, but it certainly could be possible if we, let's say, added one more odd vertex. So we have our even number of odd vertices. With this theorem, either the handshaking lemma or parity theorem, we're ready to return to the odd doors problem and solve it. So, back to our odd doors problem, let's remember the 3 details about the problem that we know. We know that the jewels are in a room that has an odd number of doors. We know that only one of the 2 labyrinths has a room with an odd number of doors. And we also know that one of the labyrinths has 2 doors leading in, while the other has 1, 2, 3 doors leading in. So the pictures below are possible labyrinths. Now they're of course not the actual labyrinths because we have no idea what the rooms, what the interior of these labyrinths look like. So these are just suggested possibilities to get our motion started with what might be going on with this problem. So let's call these labyrinths Labyrinth 1 and Labyrinth 2. Now, in most scenarios, what you need to do to try to apply graph theory is assign what is representing vertices and what is representing edges. So in this particular problem, if we let our vertices be rooms and our edges be doors, then we can build a graph based upon the pictures below. So for all of the rooms below, I'm going to put a vertex in each one of these rooms. On and on and on. Okay, so each room has a vertex, and now if a room is directly connected to another room with a door, we're going to connect those rooms or vertices with edges. So there would be an edge from that room to that room going through the door. And there would be an edge there, and an edge going there, and so on. Okay, so we got started. We've drawn our graphs inside of the labyrinths. But at this point, we haven't encompassed everything that the problem told us. We've drawn a graph inside of this labyrinth, and a graph inside of this labyrinth, but those graphs could be anything. There's really no restrictions on those particular graphs. We can't really distinguish one from the other unless we include some extra information. Let's remember, there's 2 entrance ways to one of the labyrinths and 3 to the other. So if we make an extra vertex that represents the outside and connect those doors as well, for both of these labyrinths, we now have a situation where we know that one of the vertices in this labyrinth must be of degree 2, and one of the vertices here must be of degree 3. That can help us solve the problem. I'll let you think about it for a moment, and then we'll write down the solution. Okay, so with those degrees in mind, let's think about the handshaking lemma. The handshaking lemma says that there must be an even amount of odd degreed vertices. So over here in labyrinth 1, we have discovered one even vertex. And we know that one of the two labyrinths has all of its vertices as even. So it could not be this labyrinth because we've already discovered an odd degreed vertex. So labyrinth 2 cannot have all of its vertices having an even degree. So it must be labyrinth 1 that has all of its vertices of even degree. On the other hand, let's remember the handshaking lemma for labyrinth 2. We found one odd vertex. We know that there is an even amount, so the number of odd vertices must be 2 or 4 or 6 or 8 and so on. So we know that there's at least one more odd vertex inside of the labyrinth by the handshaking lemma. So we can write that labyrinth 2 has at least one odd vertex, and therefore by using the handshaking lemma, it must have a grand total of an even amount, so 1 or 3 or 5 or 7 more to make that grand total an even amount. So that means that no matter how we've drawn this graph, if we've correctly drawn the graph, we should be able to search out another vertex with odd degree. So if you search and search, you do find that this particular vertex right here that we filled in red has an odd degree. In fact, the degree is 3. So the labyrinth that we want to dig up is the labyrinth with 3 doors, or labyrinth 2. All right, let's look at a couple more problems that have to do with the handshaking lemma or parity theorem. All right, in this example, we make up a fake university in the bustling Alberta town of Two Hills. So we're going to say that this small town has 25 professors at its university, and like any small town, gossip is spreading through the university. And the administration has decided that if too many professors are gossiping with others, nothing gets done and everyone is upset. But we can have 25 professors each talking to 5 others safely. But any more than that, confusion will spread. So to maximize the collaboration without risking the confusion, we're going to connect everyone's phone to exactly 5 others. So our question is, can this be done? So how can we use our graph theory to help us out here? What we need to assign is something to represent vertices and something to represent edges. So a professor, if connected to another professor with a phone line, will represent a vertex connecting through an edge to that professor. So the professors are vertices, and when connected by telephone, they have an edge between them. So let's see if we can build such a graph. Let's use the parity theorem to decide. So twice the number of edges is equal to the sum of all the degrees, so the sum of each degree in our graph, and we're going to cycle the vertices through capital G. Capital G will represent our graph that we're trying to build. So on the right-hand side of this equation, we know that there's 25 professors. And each professor is supposed to be connected to exactly 5 others. So 25 vertices, each with degree 5. Now, unfortunately, if you were hoping to get a graph out of the deal, on the right-hand side, we have an odd number, and on the left-hand side, we have an even number. So one way that we can represent this contradiction is to use modular arithmetic. So how about we take this number into mod 2, and we get 1 on the right-hand side. Now on the left-hand side, we get 0 because it's twice an integer. So what we have is 2 different numbers. One of them's odd and one of them's even. So we have a contradiction. The contradiction is right here at that equality. The parity theorem doesn't hold, but the parity theorem holds for every single graph. So it means that there's no such graph that can solve this problem. So can this be done? The answer is no. And the reason is that there is no such graph. All right, so let's look at the next problem. Okay, so in the Kingdom of Glee, the roads perform kind of like a graph. They don't cross over each other or they don't intersect. And in graphs, you don't sort of jump from one edge to another. So that's the intersecting part. And there's no dead ends in a graph because every edge has to end at a vertex. So we can comfortably represent this Kingdom of Glee as a graph where our cities represent vertices and the roads represent edges. Okay, so part A says that we have 100 cities, so capital V is 100, and there's 4 roads leading out of each city, and it asks how many roads are there altogether. So we're searching for capital E. That's our question mark. Let's use the parity theorem again. So twice E is equal to our degree sum, so the sum of every vertex in our graph. And we know that there are 100 vertices in our graph, and each one of those 100 vertices has 4 roads leading out. So if we multiply that by 4, we get the degree sum. So in this case, our degree sum is 400, and that means that capital E is 200. So we have our answer to how many roads are in this kingdom. In part B, we're asked a different question. So again, we're in the Kingdom of Glee, but this time the scenario is different. It's no longer 4 roads leading out of each city. It asks, what if we have 3 roads leading out of each city? Can the kingdom have exactly 100 roads? And we don't assume anymore that there's 100 cities. We don't know how many cities. That was just an assumption for part A. In part B, it's a new problem. So how about we try to use our parity theorem once again? We'll set this up so that we have twice the number of edges equal to the degree sum. And we are told that 3 roads lead out of each city, but this time we don't know how many cities there are. So we'll just label capital V as the number of cities, and each of those cities have 3 leading out, so we'll multiply by 3. Okay, now we are told that we're trying to make this particular kingdom have exactly 100 roads, so that would be the number of edges. So we would get 200 on the left-hand side, and now we have this question. Could we have 200 equal to 3 times a number? Well, this is really not possible because 200 is not a multiple of 3, but 3 times some integer is a multiple of 3. How about we use the mathematical notation of modular arithmetic to represent this contradiction? So on the right-hand side, if we take that number into mod 3, we have 0. But on the left-hand side, if we take the 200 into mod 3, we get 2. So again, we have a contradiction with the parity theorem. So the connection here is not possible because there is no such graph. Oh, thanks so much for listening. We'll see you on the next series of videos about graph theory.